Well, thank you for listening. This is part of my PhD project research. So basically, we know that in order to obtain better performance, well, usually more specialization is introduced into the instruction set architecture, sometimes in the form of instruction set extensions. There might be another way to tackle this problem, because as we know, this might not be completely scalable over time. So people have been exploring reconfigurable architectures for the last 20 years. There are different types of architectures. For example, there is the accelerator approach, where you have a relatively large FPGA fabric or reconfigurable fabric attached to the CPU, or there is also the approach where you can have some FPGA fabric embedded in a hardened CPU, and this is the case where we are exploring. So we use the term interlays as a way to refer to a small FPGA fabric that sits between the software and the physical layer. So we are looking into this, and we see that in order to have something, a prototype working, it will need we will need to build a large environment, including, for example, the design of the fabric itself, some custom compilation toolchains, maybe, the integration of configurations, which are pretty much the instructions. Also, well, the integration. But in our case, we only focus on how to integrate this fabric and how to generate custom instructions for that interlay. So what we did was to take a top-down approach where we analyzed an existing SoC system, and we asked ourselves what will happen if instead of something like the Neon, we will have a reconfigurable fabric. Our hypothesis that with a reconfigurable fabric, we could implement on top of it an implementation that is compatible with the Neon instruction set, and with this will allow us to do things like customization, in-field updates, and some other optimizations. So as we know, well, Neon is the vector engine of ARM. It has an independent vector register file and data path, and it's targeted mostly to media applications. So what we did was that we took a Xilinx sync chip that is an off-the-shelf device, and we used the floor planning tools to kind of get a sense of how big the embedded ARM is in terms of FPGA primitives. Then from that, we made a study how big the Neon unit is in terms of this ARM core, and we got to a number like this for a single Neon unit, something like 1,000 LUTs, which is the logic unit in FPGAs, the minimal logic unit. So what we did was we implemented an ALU inspired in the Neon instruction set, and we compared that implementation with the reference that we saw before. And what we saw is that in order to implement our soft Neon of the Neon instruction set, it will have to be at least 10 times larger, and it will be 4 times slower than the existing Neon. So what we did then was to do some profiling. So as we know, not all the applications use all the instructions and not all the vector lengths. So we implemented some optimizations. So we were able to reduce that gap substantially for performance and for area. But nevertheless, what we saw is that there is still a gap of around 1.23 something. So what will we implement something that is still slower for some applications? Well, because we can have some other type of applications that actually benefit from having a reconfiguration. For example, operations that perform bit manipulations that we know FPGAs are very good at that. So with that, we can have speedups from anywhere from 5 times to 70 times for some applications. Also, encryption. We analyzed encryption instructions, and we saw that for some of the cases that we analyzed, we have better throughput for some security primitives. And for completeness, we built a framework to automatically generate custom instructions. This was based on the tools already existing for FPGAs, and in a combination with Gen 5. So the idea here is, for example, that we take some of the functions of a security application, and then they just maybe swap them in time if the reconfiguration allows it. And then we look into going more realistic. So most of the time we have things like the Cortex-A9, which is a double core, so we can find it in many devices. And we used it in combination with some other techniques like partial reconfiguration. So what we have then is that we built a prototype. It started as a dual core system, and we augmented it with a CMD engine, pretty much close to what the architecture of the ARM Cortex looks like. And then, well, this is a mostly monolithic static design targeted for FPGA fabric. And then what we did was to use a tool for partial reconfiguration in order to separate a static part from a dynamic part, which is mostly just the CMD engine. And in this case, what we did was to create a sort of connection macros. And so we were able to kind of anchor the different paths for all the different instructions. So what we want to convey in this image is that we have 2 CPUs on each side of the CMD unit. And then what we have is some connection macros. This is only at the same time. But with this, we ensure that the signals from both cores are propagated to all of the slots in our design. And basically, with this, all the slots in the CMD unit get all the operands, and all of them can produce a result, and we select whatever we need. There are some good numbers for reconfiguration, slot reconfiguration, and we also are planning to hide this using prefetching. It's a technique well known for reconfiguration. And then the prototype looks kind of like this. I mean, the basic instruction set that we used for this one was RISC-V. So what we did is try to shape our design in dual core architecture. So then using handcrafted or automatically generated custom instructions, we will have an instructional library, and then different instructions will be loaded at runtime. So for the evaluation of this architecture, what we did was to generate some custom instructions, vector custom instructions, something like for motion estimation and some other operations were very well used in media. And what we did was, and what we saw was that we were able to get substantial kernel speedups. And some other thing is that the idea is that, for example, this interlay could be used, for example, for implement instructions like mailboxes, where we can have a sharing of data between 2 cores. So that's one of the features that you cannot find in some other hardened designs. And yeah, I mean, basically, what we want to convey is that our approach wants to go towards moving reconfiguration to hardened systems. So we wanted to have something realistic and that fits in an existing architecture. And with this, we just want to enable for the research. Basically, well, yeah, this is it. And for future work, we want to scale our design. So, for example, having a larger interface or the number of slots, or also explore other application domains and build some other components for this ecosystem. And basically, that's it. Thank you.
Do we have any questions?
It looks like most of what you were looking at were custom operations on vectors.
Yep.
If you did specialize just on that, such that you actually had a hard register file with forwarding, but you just had programmable combinators and that sort of thing, do you think you could do a lot better than the 10x overhead of a general FPGA fabric?
Well, for example, for the CRC, for some security primitives, yes, we can go further than 50%, 50 times. Sorry. Yeah.
I meant it takes you 10 times the area to implement Neon.
Oh, in terms of area, okay.
But if you knew I am going to be operating on vectors,
yeah,
and therefore you had hard-built a vector register file with potentially forwarding, that sort of thing, but the only thing that was programmable was the combinational logic, such that you might want to say, maybe I want a custom sorting algorithm that will sort all the bytes in this 32-byte vector. Do you have any feel for how much that would reduce your area rather than using general purpose registers and that sort of thing?
Maybe it wasn't clear, but yes, this one tries to convey that. So if you do ISAB subsetting and vector width customization, so instead of implementing all the vector lengths available, you only implement 8-bit operations, for example. Just you can drastically reduce, because you remove all the logic that is not needed. So that's it.
Any more questions? Okay, so I have a question about your choice for doing this for SIMD instructions. I mean, given that you're doing custom instructions and doing general purpose sort of reconfigurable fabrics to implement them, it seems like you may have a much larger design space open to you than sort of restricted SIMD, which is very spatial parallelism, very sort of could you not do more data paths, more data flow, deeper instructions?
Yeah. I mean,
is there a reason why you didn't consider that?
I mean, we try to also evaluate this aspect. So what we did here was basically taking, doing some profiling on an application, then simulating Gen5, and then try to extract, because we wanted to go also for data flow graphs and all these things, and then map it. But I mean, we wanted to go different because the complexity, I mean, it can grow exponentially. So we want to go, for example, this one is based on in HLS, high-level synthesis. So we wanted to avoid the complexities of going for heuristics and all these things when you go for graphs in an application. So that was the idea, going for functions instead of lower-level graphs. Yeah.
Any more questions? Okay, thank you very much. Let's thank our speaker.